Just 2 full days ago, a telescope in Chile pointed itself directly at one of the single most studied patches of sky in the history of astronomy, a region scientists have already been closely staring at since 2003. And it still managed to find something genuinely new. Before going any deeper into this release, it's worth taking a genuine moment to understand the observatory itself, along with the story behind its name, since that context explains exactly why this particular milestone matters so much to the people who spent decades building toward it. This telescope sits on a mountain called Cerro Pachon, high in the Chilean Andes, a location chosen specifically for its dry air and dark, largely cloudless skies, ideal conditions for capturing faint light from deep space. It's named after Vera Rubin, an American astronomer who decades ago studied how galaxies rotate and noticed something strange. The outer stars in these galaxies were spinning far faster than they should have been able to, based purely on the visible matter astronomers could actually see. That observation became some of the strongest early evidence for the existence of dark matter, a mysterious invisible substance that appears to make up a huge share of the total mass in the universe, even though we've never been able to observe it directly. Decades later, this observatory was built and named in her honor, designed specifically to continue chasing answers to exactly the kind of question her work first raised. The mission this observatory carries out is called the Legacy Survey of Space and Time, or LSST. After the observatory captured its very first test images back in June of 2025, and after many months of careful calibration and system checks, officials confirmed that the real survey had officially begun on June 30th, 2026. The head of the LSST project explained at the time that the decision to officially begin came only after a careful operational review covering image quality, survey speed, system reliability, and calibration accuracy, because once that 10-year clock starts running, there's no going back to quietly fix small mistakes along the way. Since February of 2026, even before the official start of the survey, the observatory had already been streaming roughly 100,000 automated alerts every single night to astronomers around the world, flagging anything in the sky that had moved, brightened, faded, or otherwise changed since the previous observation. Those early alerts had already helped confirm new supernova explosions and contributed to the discovery of more than 11,000 previously uncatalogued objects in our own solar system, all before the observatory's primary mission had even formally started. Officials have said that once the survey reaches full operational speed, that nightly alert rate is expected to climb dramatically, potentially into the millions of alerts every single night, supported by a global network of automated software systems and follow-up telescopes ready to respond to anything unusual the moment it's detected. Let's start with exactly what happened, because the timing here matters. On July 31st, 2026, the Vera C. Rubin Observatory released a brand new image of a region of sky called the Cosmos Field, short for the Cosmic Evolution Survey. This release marks something genuinely significant for the entire field of modern astronomy. It was Rubin's first official LSST camera image and catalog release specifically produced for real scientific research use, an event the observatory is formally calling Early Data Preview 2, or EDP2 for short. Up until this exact point, everything Rubin had shown the general public, all the earlier images released back in 2025, were essentially test shots taken during a genuinely long commissioning and calibration process, meant to make absolutely sure every single part of the telescope was working correctly before the real 10-year survey could officially begin. This new Cosmos Field release is genuinely different from all of that earlier commissioning work. It's built from real science validation observations, carefully collected between April of 2025 and January of 2026, and it represents the observatory's very first real step into actual ongoing scientific data collection and public release. So why did scientists choose the Cosmos Field specifically for this milestone out of every possible patch of sky they could have picked anywhere across the entire observable universe? Because this particular patch of sky, located in the constellation Sextans, is not some random unexplored region chosen simply for convenience. It is one of the most heavily studied areas of the entire observable universe. The Hubble Space Telescope spent from 2003 to 2005 staring directly at the same patch of sky, and in the decades since, it has become something close to a scientific reference point, a kind of laboratory for studying galaxies, precisely because so many different telescopes and research teams have already gathered so much data on it. Before Rubin ever pointed its camera there, astronomers had already identified more than 2 million individual galaxies within the Cosmos Field using previous surveys. Scientists picked this region specifically because it can be observed both from the ground and from space, and because having so many previous independent observations of the exact same patch of sky gives researchers an extremely reliable way to check whether Rubin's new data lines up correctly with everything astronomers already know. In other words, before trusting Rubin with entirely new, previously unexplored regions of the universe, Scientists first pointed it at the one place in the sky they already understood better than almost anywhere else, specifically to prove the new machine works exactly as intended. And it clearly does. The new image Rubin produced of the cosmos field was built by stacking together hundreds of individual observations, all taken using the observatory's LSST camera, the same 3,200 megapixel camera that remains, to this day, the largest digital camera ever built by human beings, an instrument years in the making, developed specifically to make an achievement exactly like this one possible on this kind of enormous scale. Packed into this single combined image are more than 500,000 individual galaxies, along with more than 50,000 individual stars. Within that enormous population of galaxies, astronomers can already pick out an incredible variety of different types. Delicate spiral galaxies with sweeping arms of stars, smooth rounded elliptical galaxies, chaotic distorted galaxies caught in the middle of merging together, and extremely faint, extremely red galaxies belonging to some of the most distant reaches of the observable universe. Because the cosmos field happens to contain relatively few bright foreground stars from our own Milky Way, astronomers actually get an unusually clear, unobstructed view straight out into deep space, without nearby stars cluttering up the picture the way they often do in other parts of the sky, allowing this particular image to showcase an especially wide and representative variety of distant galaxy types in one single unified frame. Exactly the kind of diverse test case scientists wanted for this specific milestone. Now here's where the actual scale of this achievement becomes clear. This single cosmos field image is only a small sample, a preview of a much larger dataset released alongside it. Along with the image itself, Rubin's Early Data Preview 2 provides the scientific community with a full deep co-added, meaning stacked and combined, a view covering 3,000 square degrees of night sky. To put that number in perspective, that's roughly a sixth of the entire visible southern hemisphere sky, covered in this single data release, all from observations taken before the official 10-year survey had even properly started. And this is genuinely just the beginning. Now that Rubin's primary 10-year mission is fully underway, the observatory is capturing around 700 separate high-resolution images every single night, continuously and methodically working its way across the entire visible southern sky, then circling back to do it again just a few nights later. It's worth comparing this new Cosmos field release to Rubin's very first widely publicized image, something the observatory nicknamed the Cosmic Treasure Chest, released back during the original First Look event in June of 2025. That earlier image focused on the southern region of the Virgo cluster, the nearest large collection of galaxies to our own Milky Way, sitting about 55 million light-years away from Earth. It was built by combining 1,185 separate exposures, captured over just 7 nights of observing time, and it revealed roughly 10 million individual galaxies packed into a single 15 square degree section of sky. At the time, scientists pointed out that even that huge number, 10 million galaxies in one image, represented only about 0.05% of the roughly 20 billion galaxies Rubin expects to eventually capture across its entire 10-year survey. That earlier image was genuinely spectacular, but it was still fundamentally a demonstration, a proof of concept captured during commissioning before the telescope's full scientific pipeline, calibration systems, and cataloging software had been fully validated for real, publishable science. The new Cosmos field release is a different kind of milestone entirely. It's the moment Rubin's actual scientific data processing system, the software responsible for turning raw captured light into a verified, structured, searchable catalog that professional astronomers can immediately build research on, was formally proven to work as intended. And it's worth pausing on how remarkably international and remarkably open this entire project actually is. All of the raw data captured by Rubin travels from the mountaintop in Chile to a data facility in the United States, hosted at the Department of Energy's SLAC National Accelerator Laboratory, where it becomes available to the wider global scientific community. One of the primary science teams working with this data is called the Dark Energy Science Collaboration, a group of researchers spread across dozens of institutions worldwide, specifically tasked with using Rubin's observations to make extremely high accuracy measurements of the universe's fundamental properties, the precise numbers describing exactly how fast the universe is expanding and how matter is distributed throughout it. Perhaps most remarkably, scientists have pointed out that this represents the first time in the history of astronomy that this much high-quality observational data will be made available to so many researchers simultaneously. Astronomers accessing this data won't need expensive specialized equipment or their own supercomputers. They'll simply log into something called the Rubin Science Platform through an ordinary internet browser, meaning a researcher at a small university with limited funding has essentially the same access to this treasure trove of information as a researcher at one of the largest, best-funded institutions in the world. Over the full 10 years of the survey, the observatory is expected to generate roughly half an exabyte of total data, an amount so enormous that entire teams of engineers have spent years specifically building the automated algorithms needed to detect, measure, and catalog every single astronomical object contained within it without requiring a human being to manually review each one individually. Let's put the sheer speed of this operation into perspective, because it's honestly a little hard to wrap your head around. Each individual exposure captured by the LSST camera covers a section of sky equivalent in size to about 45 full moons side by side, and the camera captures a brand new exposure roughly every 40 seconds throughout the night. Multiply that pace across an entire decade of continuous operation, and you start to understand why officials have said that Rubin Observatory is expected to gather more astronomical data in just its first single year of operation than every other optical telescope on Earth has collected throughout the entire history of astronomy combined. Not close to that total. Greater than it entirely by a wide and genuinely meaningful margin. That's not a minor technical improvement over previous telescopes. That's an entirely different category of scientific instrument. Let's talk for a moment about the actual machine responsible for all of this, because the engineering here is genuinely remarkable. The LSST camera sits mounted on top of Rubin's 8.4 meter wide primary mirror, itself attached to what's officially called the Simoni Survey Telescope. The camera's imaging sensor is made up of 189 individual CCD chips, precisely arranged together into one enormous unified array capable of capturing 3,200 megapixels in a single exposure. The entire camera weighs around 3,000 kilograms, roughly 6,600 pounds, and is genuinely close to the size of a small car, an almost unbelievable piece of engineering when you consider the level of precision required to keep an instrument that massive perfectly stable and perfectly focused while capturing extremely faint, extremely distant light. Here's what makes Rubin fundamentally different from basically every other major telescope currently in operation, and why this particular achievement matters so much. Most large telescopes are built to focus narrowly, staring intensely at one small patch of sky for a very long time to gather as much light as possible from one specific target. Rubin was built to do the opposite. It is designed for speed and coverage above almost everything else, capturing enormous sections of sky quickly, then returning to that exact same spot again and again over the following days, months, and years. Over the full 10-year run of the legacy survey of space and time, the observatory will revisit every single region of its visible sky roughly 800 separate times. That repeated revisiting is exactly what allows Rubin to do something almost no other telescope can: build a genuine, continuously updating time-lapse movie of the changing universe, rather than just a single static photograph frozen at one particular moment. This dual identity, an instrument capable of both extremely wide, sweeping coverage and, through repeated revisits, extremely deep cumulative detail, is precisely what made Cosmos such a logical choice for this particular milestone. It gave the science team a region where Rubin's speed and breadth could be tested against decades of existing deep and narrow observations from other instruments, essentially checking Rubin's work against the most rigorously verified scientific homework already available anywhere in the sky. This is also exactly why the Cosmos field specifically was chosen to receive extra observational attention going forward. Because of its scientific value as such a heavily cross-referenced, well-understood region, Cosmos is going to be observed noticeably more frequently than most other areas covered by the full 10-year survey. With those additional future observations, Rubin's view of Cosmos is expected to grow even deeper over time, gradually revealing fainter, more distant galaxies and finer structural details than what's visible in this very first release. In a sense, what was just published on July 31st is genuinely only the opening chapter of Rubin's relationship with this particular patch of sky, not the final word. It's also worth understanding exactly how astronomers plan to actually use this new data, because a picture, however spectacular, is really only the starting point. Alongside the image itself, Rubin released a full scientific catalog, meaning a structured, searchable dataset listing the precise position, brightness, shape, and color of every single galaxy and star identified within the observed region. Researchers around the world will use this catalog to study how galaxies grow and change shape over cosmic time, to measure how galaxy clusters and larger cosmic structures form and evolve, and to refine our overall understanding of how matter is distributed throughout the universe. Work that directly supports Rubin's broader long-term goal of helping scientists finally pin down the true nature of dark matter and dark energy, the two biggest unsolved mysteries in all of modern physics. One of the specific techniques researchers plan to apply extensively to this kind of data is called weak gravitational lensing, a subtle effect where the combined gravity of galaxies and dark matter sitting between us and much more distant background galaxies very slightly bends and distorts the light passing through on its way to Earth. Because this distortion effect is so faint and so subtle for any single galaxy, scientists need to statistically analyze the shapes of millions upon millions of galaxies at once to reliably detect the pattern. Which is exactly why a dataset containing more than 500,000 galaxies in a single early release, drawn from a survey that will eventually chart something like 20 billion galaxies in total, is so scientifically valuable. Because the cosmos field has already been so extensively studied by other telescopes and other research teams over more than 2 decades, this fresh Rubin data can immediately be cross-checked, compared, and combined with a massive existing body of previous research, dramatically accelerating how quickly scientists can turn these new observations into genuinely new, verified scientific conclusions, rather than spending years simply confirming the new instrument is trustworthy before real research can even begin. Beyond dark matter and dark energy, this same cosmos field catalog is expected to support research across a genuinely wide range of other scientific questions as well. Astronomers will use it to study how supermassive black holes at the centers of distant galaxies grow and evolve over billions of years, to trace how galaxies collide and merge with one another over cosmic time, and to identify rare, unusual objects hiding within that population of 500,000 cataloged galaxies, objects that might otherwise have gone completely unnoticed if a smaller, less comprehensive survey had been conducted instead. Because Rubin plans to revisit the cosmos field more frequently than most other regions of sky throughout the full 10-year survey, researchers will also be able to track subtle changes in brightness across the same specific population of galaxies over time, potentially catching flaring supermassive black holes, exploding supernovae, or other short-lived, rapidly changing astronomical events unfolding in real time within a region of sky that has already been mapped in this much foundational detail. It's worth pausing here to understand why a testing strategy like this actually matters, rather than simply accepting it as a formality. Building a telescope this large, this fast, and this automated involves an enormous number of individual systems that all have to work together flawlessly. The optics, the massive digital sensor array, the software that stacks and calibrates every exposure, and the cataloging pipeline that turns raw pixels into a structured, searchable list of galaxies and stars. Any one of those systems could introduce a subtle error, a slight miscalibration in brightness measurements, a small distortion in galaxy shapes, a missed object hiding at the edge of detectability. Pointing a brand new instrument at a genuinely unexplored patch of sky first would make catching those kinds of errors nearly impossible, because there would be nothing reliable to compare the results against. By instead choosing a region already mapped in extraordinary detail by Hubble and dozens of other survey programs over more than 2 decades, Rubin's team gave itself an actual answer key. If the new data disagreed with what was already known and independently verified, that would be a clear signal something in the pipeline needed fixing before the telescope could be trusted anywhere else. The fact that Rubin's numbers lined up as well as they did against that existing body of research is exactly what gave scientists the confidence to treat this release as the genuine beginning of the survey's real scientific output, rather than simply another impressive but unverified image. The alert system behind all of this deserves a closer look too, because it represents its own significant engineering achievement sitting quietly underneath the more visible headline numbers. Every time Rubin captures a new image of a patch of sky it has already photographed before, automated software immediately compares the new exposure against the previous ones, searching for anything that has appeared, disappeared, moved, brightened, or faded since the last visit. That comparison has to happen fast, within minutes, so that any genuinely urgent event, a nearby supernova, a newly discovered near-Earth object, a flaring black hole, can be flagged and shared with astronomers around the world while it's still actively happening. Doing that reliably, night after night, across roughly 700 new images and an enormous archive of historical comparisons, requires machine learning systems specifically trained to separate real astronomical events from the ordinary noise of instrument artifacts, cosmic ray hits, and minor atmospheric distortions. Officials involved with the project have pointed out that even during the early testing period, before the survey's rate of alerts had scaled up to its expected full speed, the volume of data already being generated each night was more than any team of human reviewers could possibly process manually. That automated filtering layer isn't a convenience. It's the only reason a project operating at this scale is functional at all. Read that again, because it's easy to breeze past just how significant the cosmos field's role in verifying that alert pipeline actually is. A region this heavily studied, this well understood, gives the automated systems checking for changes an enormous baseline of confirmed, stable objects to measure against, making it far easier to confirm the alert software is correctly distinguishing between a genuine transient event and a simple processing error. Every galaxy in that catalog that behaves exactly as decades of previous observations predicted it should is one more confirmation that the underlying detection system can be trusted once it's turned loose on entirely unexplored regions of sky where no such answer key exists. There's also a quieter, more human side to this particular release worth mentioning. Alongside this scientific announcement, one of the leaders at Rubin Observatory specifically acknowledged the recent severe storms that struck the Coquimbo region of Chile, the same general area surrounding Cerro Pachon, where the observatory itself is physically located. In the statement accompanying the release, the team noted that the observatory's thoughts were with its own staff and with the broader local community affected by that damage, and specifically dedicated this particular Cosmos field image, marking the true beginning of Rubin's real scientific mission, to the people of the Coquimbo region as a small gesture of gratitude for the community's decades of support toward astronomy and toward the broader observatory complex that calls that mountain range home. It's a reminder that behind even the most advanced, most cutting-edge scientific instrument ever built, there remains a very real, very human community living and working right alongside it, in the same mountains, under the same skies, and that the people who spent decades supporting this project on the ground, long before a single scientific image was ever published, are very much part of this story too, not just the engineers and astronomers whose names typically appear in the headlines. It's a small detail, easy to miss inside a press release focused primarily on galaxy counts and camera specifications, but it says something meaningful about how this project has chosen to mark one of its most significant scientific milestones by pausing to acknowledge the community that made the entire thing possible in the first place, rather than treating this purely as a technical achievement disconnected from the place and the people surrounding it. So what should you actually take away from all of this? Not that Rubin found some singular, shocking secret hidden in deep space, but something arguably more important for the future of astronomy as a whole. Rubin just proved, using real collected data rather than test observations, that its entire pipeline works exactly as designed, from capturing raw light with the largest camera ever built, all the way through processing, stacking, cataloging, and finally releasing that data to the global scientific community on one of the most demanding, most heavily scrutinized test cases available anywhere in the sky. 500,000 galaxies cataloged and released, covering just one small corner of a much larger survey that will eventually stretch across a full sixth of the entire visible sky and beyond, all captured before the observatory's primary 10-year mission had even fully ramped up to its regular nightly pace. If this is what a single early data preview looks like, built from less than a year of accumulated science validation observations, it's genuinely difficult to overstate what 9 more full years of continuous nightly, full-speed observation are eventually going to reveal about the structure, history, and ongoing evolution of the entire universe. This is also very much just the first of what officials have described as an ongoing series of scheduled data previews and full annual releases planned throughout the survey. Rubin's early data preview 2 specifically builds on an earlier, smaller preview released prior to this one, and it will eventually be followed by the observatory's first full official data release, expected to arrive once enough of the actual 10-year survey has been completed to support the kind of large-scale, statistically robust scientific studies the mission was ultimately designed to enable. Each of these successive releases is expected to cover progressively larger areas of sky, incorporate progressively more individual observations of each region, and reveal progressively fainter, more distant objects than the release before it, gradually building toward the observatory's ultimate goal, a complete, continuously updating 10-year time-lapse record of the entire visible southern sky, built from roughly 800 separate visits to every single region it observes. Every single night from here forward, Rubin Observatory is going to keep capturing roughly 700 new images, methodically working through its list of sky regions, circling back to revisit each one again and again throughout the decade ahead. Somewhere within that constant repeating stream of images, hiding among galaxies that have already been photographed hundreds of times before, there's a very real chance this same observatory eventually catches something nobody has ever properly documented. A supernova exploding in real time, a previously unknown asteroid tracing a new path through our own solar system, or some entirely unexpected astronomical event that simply hasn't happened, or hasn't been witnessed, during the entire recorded history of human astronomy up to this exact point. That is precisely the promise behind building a telescope designed not to look once, but to keep watching patiently, night after night, for an entire decade straight, gradually turning what used to be a series of isolated snapshots into something closer to a genuine living record of the universe, as it actually changes and evolves right in front of us. It's worth remembering just how unusual this approach actually is within the broader history of the field. Astronomy has traditionally been built around the idea of choosing a target, aiming a telescope at it, and gathering as much detail as possible about that single object before eventually moving on to something else. Rubin inverts that entire process. Instead of choosing what to look at first and hoping it turns out to be interesting, it photographs essentially everything, repeatedly, and lets the interesting discoveries surface naturally out of the accumulated record, whether that's a subtle gravitational lensing signal buried inside 500,000 galaxy shapes, a hidden ninth planet revealed only through the warped orbits of distant icy bodies, or a supernova caught within hours of igniting, simply because the telescope happened to already be looking in that direction on schedule. The Cosmos Field release is a small, carefully chosen proof of exactly how well that inverted approach actually works when tested against decades of existing, independently verified science. Every galaxy already cataloged by Hubble and other observatories over the past 2 decades gave Rubin's team a way to check its own numbers, its own measurements, its own automated cataloging software against a body of knowledge nobody could seriously dispute. And having passed that test on one of the most scrutinized patches of sky in existence, the observatory now moves forward carrying something more valuable than any single image, a confirmed working process capable of doing the exact same thing across the entire visible southern hemisphere, night after night, for the better part of the next decade. There's a broader pattern worth noticing in how this entire project has been rolled out, one that separates it from almost any previous astronomical instrument. Rather than building the telescope, running it in secret for years, and eventually publishing a single landmark discovery, the team behind Rubin has structured this as a series of escalating, publicly documented checkpoints. First light images during commissioning, an early alert stream during science validation, and now a fully cataloged scientific data release built and tested against one of the best understood patches of sky available anywhere. Each checkpoint has been used deliberately to build confidence, both inside the scientific community and among the wider public, that the instrument works exactly as intended before it's trusted with genuinely unexplored territory. That approach reflects just how much is riding on this single observatory functioning correctly for the full decade ahead. Unlike a mission built around one specific target or one specific question, Rubin's entire value depends on the reliability of its automated pipeline being maintained consistently across billions of individual measurements spread across 10 years of continuous operation. A single, quiet, unnoticed calibration error early on could quietly distort an enormous portion of the survey's later scientific conclusions, which is exactly why so much care has gone into proving, step by step, checkpoint by checkpoint, that every part of this system can be trusted before the observatory is allowed to turn its full attention toward the vast, mostly uncharted regions of sky still waiting to be properly mapped for the very first time. For now, the Cosmos Field stands as proof that the machine works. What comes next, night after night, region after region, for the next 9 years, is the actual survey this entire project was built to carry out. And the Cosmos Field release is simply the moment everyone watching finally got confirmation that it is ready to begin. Every future headline about this observatory, every new asteroid, every distant supernova, every fresh clue about dark matter or dark energy will trace back to the same verified pipeline, quietly proven correct on a patch of sky in the constellation sextans that astronomers have now trusted for more than 2 decades